In this unit, we're going to be working with polynomial functions and their characteristics, and today we are going to identify polynomials and name them based on their degree and number of terms. A polynomial function is a function comprised of a monomial or a sum or difference of monomials. So let's talk about what a monomial is. A monomial is what we normally think of as like a term in an expression, and it's factors that are connected by multiplication. Those factors could be numbers, like a coefficient, 3, and variables. And you could even have exponents because exponents imply repeated multiplication. But notice that there is not a plus or a minus in this monomial expression. The 3 and the x's, the x times x times x times x, they are all connected by multiplication. And so when you string together more than one monomial with a plus or a minus, that becomes a polynomial. So a polynomial has to have two specific things. It has to have real number coefficients. And so let's talk about what real numbers are. Real numbers are any numbers that we know that are not imaginary. Okay, so almost anything we could think of, any number in the real world. We have to have whole number exponents, and that's a little bit more specific because whole numbers are like 0, 1, 2, 3, etc. When we look at a polynomial function, oh, I left out one more thing. I wanted to add this one on here. I don't know why it's not on there, but you can't have any variables in the denominator. No variables in the denominator of a fraction. And this one, it sort of is tied in with the exponent situation because a variable in the denominator represents a negative exponent. But we haven't really talked about that recently. And so I just want to remind you that a variable in the denominator is not allowed. So let's look at example 1 and see if it fits the characteristics of a polynomial function. First, we're going to look at the coefficients. So the coefficients are the numbers in front of the variables. Here there's an understood 1 in front of x to the third, and then there's a 3 in front of x. Those are both real numbers, so we're good there. Our coefficients are real. And now we will look at the exponents. So our first exponent is a 3, and our second exponent is an understood 1. And those are both whole numbers. And we don't even have any fractions here, so there's no variables in our denominator. So this is a polynomial function. Let's look at B. We'll do the same thing. Look at the coefficients first. We have an understood 1, a 3, a -2, and a -5. Actually, that -5 is holding up that exponent, so it's really a base. But we have all real numbers there, so let's look on to our exponents. We have a 4, we have an understood 1, we have a 2, but here we have an x. And we can't have a variable as our exponent. That is not a whole number. And so this is not a polynomial function. All right, let's look at example C. We'll look at our coefficients again. We have a 6, a -2, and an understood 1 right there. And then our exponents, we have a 4. Oh, we have a -1 here. So we can't have a negative number because that is not whole. And so this is also a no. And last one, real number coefficients, -0.5, that is real. Pi, it's not very pretty, but it's real. And then negative radical 2, also irrational, just like pi, but it's still a real number. So those are all legal. Let's look at our exponents. Here in the first term, we do not have an x factor. This is like -0.5 x to the 0 power. So our exponent is 0, and understood 0. That's still a whole number, so that's okay. So we have an exponent of 0 here. We have an exponent of 2 here, and then we have another 0 power here. We have like x to the 0 as well. So 0, 2, and 0, those are all three whole numbers. And so this is a polynomial function, even though it's kind of weird. And then I wanted to throw another one on here just to give an example of something you might see that would also, well, spoiler alert, this is a deal breaker. So x to the third plus 8x squared plus 1 over x. And again, we haven't talked a lot about exponents and rules of exponents and properties of exponents this year, so you may not remember, but if you have an x on the bottom of a fraction, what it really means is the x is to the negative 1 power, and we cannot have a negative exponent on our polynomial function, and that negative exponent is causing this x to be in the denominator, so this one is also a no. So just, that's what you're on the lookout for: real number coefficients, whole number exponents, and no fractions that have variables on the bottom. A polynomial is in standard form when the exponents are in decreasing order. The degree of a polynomial is the exponent of the greatest power term. The leading coefficient is the coefficient of the greatest power term. And the constant, or a constant, is any number with no variable. So for example 2, we are going to practice writing in standard form and identifying these things about a polynomial. Here we go. Start with g of x equals, and we want to find our highest power term first. So the highest power looks like that is 4. So we're looking at negative 3x to the fourth as our first term. Then the next higher power term is the third, so plus 12x to the third. Then 2x squared. Oops, I didn't get my 12 there. There we go. And then finally, negative 4. So that is our expression in standard form. And then we're going to look at the degree. The degree is the exponent of the greatest power term. So our greatest power term was 3x to the fourth. Sorry, negative 3x to the fourth. So the power of that is 4. So the degree of this polynomial function is 4. So again, we're looking at this exponent. That's the degree. Alrighty, then our leading coefficient is the coefficient on that same term, which is negative 3. And then finally, the constant is the plain number that has no variable, which is negative 4. All right, let's look at B. This one only has 2 terms. We have a negative x and a 3, and they need to switch places in order to be in standard form. So h of x equals negative x plus 3. The degree is the power on the highest power term. So we're looking at this first term, and it has a power of understood 1. So our degree is 1. The leading coefficient is the coefficient on that term, which is an understood negative 1. And the constant is 3. Now, if you look at example 3, we're going to talk about how we can classify polynomials by degree and number of terms. I think we've already mentioned monomial. That's a polynomial that has 1 term. Mono is a prefix that means 1. And you've graphed in Algebra 1, you graphed linear functions and you graphed quadratic functions. Those were named based on the degree of the function. So let's talk about how we name some polynomial functions. In this first polynomial function, f of x equals 12. We only have a 12, we do not have a variable, so it's like our variable is x to the 0 power. Anything to the 0 power equals 1. So x to the 0 is 1, and 1 times 12 is 12. So we have an understood x to the 0 power there. This has 1 term. And so we will name it a monomial. Mono meaning 1. The degree is our power, which is 0. And when we have a degree of 0, we call it a constant. We do not have a variable, just a number with no letters, okay? Looking at the next example, we have 8x, that's one term again, not separated by a plus or a minus. So we will name it also a monomial. Here, our degree is a 1, and we call polynomials with a degree of 1 linear. Next example, we have two terms here, and we call those binomials. Kind of like a bicycle has two wheels, a binomial has two terms. Our exponent, or our degree, is 2. And we call functions with a degree of 2 quadratic. For g of x, we have two terms again. So we'll call that a binomial. And looking at the degree, the highest power is 3, and we call those cubic. Next example, h of x, we have 3x squared minus 4x plus 6, that's 3 terms. And we call those, you probably guessed it, trinomials. Like a tricycle has 3 wheels. And our power, or our highest exponent, is 2. So back to quadratic again. For s of t, we have 1, 2, 3 terms again. And our degree is 4. So we call that quartic. Like 4 quarts in a gallon, or 4 quarters in a dollar. And for f of x at the bottom, 1, 2, 3, 4 terms. Anything with 4 terms or more, we just call a polynomial. And then our degree here is 3. And again, 3 is called cubic. So looking at our list here, if you're wanting to make note, if the degree is 0, we call it constant. If the degree is 1, we call the polynomial linear. If the degree is 2, we call it quadratic. If it's 3, we call it cubic. And if it's 4, we call it quartic. And then 1 term is a monomial, 2 terms is a binomial, 3 terms is a trinomial, and 4 or more is a polynomial. So that's how we can name polynomials by degree and number of terms. It's kind of like giving your polynomial a first and last name. We usually name it by degree first and then by number of terms. So for example, if I was looking at g of x right here, I would call it a cubic binomial. Next, we're going to work on operating with polynomials. For most students in Algebra 2, this will be a review, but it's helpful to go back and think about the things we learned in Algebra 1. For some of us, it's been a couple of years. So first, we're going to be adding polynomials, and of course, we will be seeing a plus between the 2 polynomials or 3 polynomials or more. So the first thing that we want to do is combine like terms. And when we combine like terms, we add the coefficients of terms that have the same variable raised to the same exponent. And when you combine them, the result is a like term. Sometimes students are tempted to somehow combine their exponents when they also combine their coefficients, but keep in mind that they are like terms and the answer is also a like term. You are just gathering them together. And then once we've combined our like terms, we will write our result in standard form. All right, so let's take a look at example A. We have 2x to the third, and I don't see any other third power terms. So I'm going to write this term down. I don't have any terms to combine it with. And I like to add mine going in descending order so that it's already in standard form when I'm finished. So next would be 2x squared, and I don't see any other x squared terms. So I'm going to write that one down, and I also like to mark them out as I go. All right, then x to the first power would come next, and I have two of those. I have 7x and negative 8x. That gives me negative 1x. And so those are done. And then finally I have negative 4 plus 1, which is negative 3. So minus 3. So since I chose to combine my like terms in order, my answer is already in standard form. And that just keeps me from having to do an extra step, but you do not have to do it that way if you don't want to. On example B, we'll do the same thing. So we have 5x to the fourth and 1x to the fourth, which gives us 6x to the fourth. And then our next power would be 12x squared. And then we would bring down the x, which has no like terms as well. And finally, the negative 10. So we're just adding the coefficients, and we're keeping the variable and exponent the same. So the sum of 5x to the fourth and 1x to the fourth gave me 6x to the fourth. All right, let's look at subtracting, which is basically the same idea. But with subtracting, we have to distribute the negative first. And this seems to throw students off a little bit because they don't want to take the time to write it down. But after you change your signs, then you're going to combine like terms and write your result in standard form, just the same as you did with adding. An important thing to note is when you distribute the negative, all the signs that follow will change. Here we go. Example C, I'm going to rewrite the problem distributing the negative. So 7 minus 4x squared minus x, those didn't change. But following the negative, or the minus sign that tells me I'm subtracting, I'm going to distribute, which makes this a minus 3x squared, a minus x, and a minus 12. So now I have written it out with the signs all changed. Notice I had a positive 3x squared and that became negative. I had a positive x and that became negative. I had a positive 12 and that became negative. Now I'm ready to combine my like terms. So the highest power term I have is x squared. I have negative 4 and negative 3, so that gives me negative 7 x squared, negative 4 and negative 3. And then I have two x terms. I have negative x here, and I have a negative x here, which gives me negative 2x. So those are gone, negative x and negative x. And then I've got constants. I've got a 7 minus 12, which is negative 5. For example D, I'm going to do the same thing. So that's going to give me 6x squared minus 3 minus 2x cubed minus 5x squared plus 9x minus 8. Alrighty, so I'm ready to combine like terms again. I only have one x cubed term, and that's negative 2x cubed, right there. I have 6x squared minus 5x squared, which is positive 1x squared. Then I have a positive 9x, and I have negative 3 and negative 8, which gives me negative 11. On to multiplying. We've been working with multiplying a bit already because we've been factoring, and factoring is the opposite of distributing. So now we're going to be distributing, which is the opposite of factoring. So you can see the first thing we're going to do is distribute each term from one polynomial to each term in the other. And then we'll combine like terms and write the result in standard form as we did above. Here I have a monomial, one term, times a polynomial that has 3 terms, a trinomial. So I'm going to have to distribute that negative 2x 3 times, once to every term there. Negative 2 x times 5x squared is negative 10x to the third. Next, negative 2x times negative 3x is positive 6x squared. And then finally, negative 2x times 1 is negative 2x. And my powers are already in descending order, and so this is in standard form with no like terms. Now this next one, I have a binomial times another binomial. So I'm going to have to multiply each of the terms in the first quantity to each of the terms in the second quantity. Sometimes we call this FOIL, or double distributing. I should have 4 terms when I distribute, then I'll combine like terms as needed. So first I'm going to start with the 3x and multiply it to the 2x, and that gives me 6x squared. And then I'm going to multiply that 3x to the 1, positive 3x. So now I've distributed the 3x to both terms. And now I'll do the same with the negative 4. Negative 4 times 2x is negative 8x, and negative 4 times 1 is negative 4. Usually, if you have a kind of a standard binomial times a binomial, your 2 middle terms will be like terms, and so we'll combine those to get 6x squared minus 5x minus 4. All right, now this next one has a binomial, 2 terms, times a trinomial, 1, 2, 3. So we should end up with 6 terms when we distribute. And there are a couple different ways we can do this, but I'll go ahead and start with just basic distributing. All right, so I'm going to distribute my negative 3x to 4x squared, and that gives me negative 12x to the third. And then negative 3x times x gives me negative 3x squared. Negative 3x times negative 9 is positive 27x. Now I'm ready to distribute my positive 2. And sometimes students like to go ahead and write the like terms underneath their like terms so they can add them vertically. So I will show you how to do that here. So 2 times 4x squared is 8x squared, and I'm going to write that positive 8x squared underneath its like term. And then 2 times x is positive 2x, and 2 times negative 9 is negative 18. And then instead of having to look across, you can just look vertically and add your columns. Negative 12x cubed plus 5x squared plus 29x minus 18. And we're done. You can also do this one using the box method. I've showed you how to do that with a binomial times a binomial. You can multiply any types of polynomials together this way. So for that particular one, you would make a 2 by 3 box, and you would put your binomial on the 2 boxes like this, and your trinomial on your 3 boxes like this. And where the 2 terms meet up, that's where you multiply them. So negative 3x times 4x squared gives you negative 12x to the third. 2 times 4 here gives you 8x squared. 2 times x here gives you 2x. Negative 3 times x here gives you negative 3x squared. Negative 3 times negative 9 gives you 27x. And 2 times negative 9 gives you negative 18. So you see I have all of the same terms. They're just written in a different way. Oftentimes this is kind of nice because your like terms, not always, but often, will kind of line up diagonally in this way. So you see I have the same first term, 12x to the third, that I had here. And when I combine 8 and negative 3x squared, I get the same 5x squared. 27 plus 2 gives me the same 29x, and then my negative 18 at the end. So you can do it that way if you like the structure of it, and some students do. All right, and then these last couple, these are asking us to take the whole quantity and multiply it times itself. So h, it's squared, meaning that we're going to multiply 2x plus 5 times itself once. And then on I, it's cubed, so we're going to multiply x plus 3 times itself 3 times. All right, so here we go. I'm going to kind of scoot this one down here. So 2x plus 5 times 2x plus 5. And it is a common error for students to think that they can just take this exponent and apply it so that this becomes like 4x squared and 25. But that is wrong, wrong, wrong. You cannot apply an exponent into a quantity that has a plus or a minus inside. We have to expand it out and multiply it out using distribution. All right, so here goes. 2x times 2x gives me 4x squared. 2x times 5 gives me positive 10x. I'm going to get another one of those. And then I'm going to get positive 25. And that gives me 4x squared plus 20x plus 25. You may notice that this is a perfect square trinomial. And you may recall this type of expression from our factoring unit, and we also created these when we were completing the square. So if you notice that pattern and you think about it, that 2 times 5 is 10, and that middle term is double that, you could skip the FOIL part of it, or the double distributing, and go straight to the answer, but you can always just FOIL it out to get the answer as well. All right, last one. We haven't really done any examples like this so far this semester. We're going to multiply x plus 3 times x plus 3 times x plus 3. And really, the way that you have to do it is to work on 2 of them and multiply them together first, and then take the third one and multiply it to the product of the first 2. Okay, notice that I highlighted the second and the third. That's because I want to keep, this is just personal preference, I like to keep the binomial at the front and then multiply that with whatever I get when I do these 2. All right, so when I multiply these 2 together, I get x squared, 3x and another 3x is going to give me 6x, and then 9. So that's what I get here, x squared plus 6x plus 9. Then I'm going to take, so that came from there. Then I'm going to take my binomial times the trinomial. So x cubed plus 6x squared plus 9x here. And then the 3x squared plus 18x plus 27, and then I'll write it in standard form. So x cubed, 9x squared, 27x, and 27. And as tedious as that seems, I do know a little shortcut for that, and we're going to be working on that coming up in the next couple of days using Pascal's triangle. Okay, so that's operating with polynomials. I don't think it's new to most of you, but it's always good to practice. Common errors are forgetting to distribute the negative, that's a big one. Changing the exponents when combining like terms. Then also it seems that students have a hard time memorizing these degree and number of term names. So just practice that over the next couple of days and make sure that you have those memorized. You have some practice at the bottom of the page and on the next page as well. Good luck.